about the derivatives of the trig functions. So on Wednesday, we reviewed some of the basics of trig functions in general, and today we're going to talk about their derivatives. So this is a graph of y equals sine of x. It's got a period from 0 to 2 pi, range -1 to 1. We don't have a way to come up with a formula for its derivative yet, but we can sketch the derivative of any function. Right? So I'm going to try to sketch the derivative of this function, remembering that when you sketch a derivative, you're sketching points that are of the form x comma slope, right? So at pi over 2, when x is pi over 2, what's the slope of the tangent line? 0. So I put a 0 at pi over 2. Okay. Are there any other places where the slope is 0? 3 pi over 2. So I put a 0 here. Okay. Looking at x equals 0, what does it look like the slope of the tangent line is there? It's positive, yes, and because the graph is increasing, and it looks like the line y equals x, right? It looks like it has a slope of 1. So if I plot a slope of 1, 0, 1, okay. And then how about here at pi? What does the slope of that line look like? -1. And at 2 pi, what's that slope look like? 1. If I connect these with a nice smooth curve, oh my God, what did I just draw? A cosine function. So this gives us a really big graphical hint that the derivative of sine is cosine. So that is our theorem. Amazing connection between the trig functions, that cosine is the derivative of sine. So we can prove this more rigorously than just by drawing the picture, but it depends on these two limits. The limit as h goes to 0 of sine h over h, and the limit as h goes to 0 of cosine h minus 1 over h. So for both of these, what happens if I just plug 0 in? Get sine h over h. If you just plug 0 in, what do you get? Undefined. Why? 0 in the denominator, which doesn't necessarily mean we can't take a limit, right? If the denominator is getting really small, we can still think about the limit. So it's not the 0 in the denominator that makes it undefined. It said both of them are 0. 0 over 0 is a limit that we can't take, right? Because if the numerator was constant, like if this was going to 5 over 0, we would say the limit was going to infinity, right? Because if the denominator is getting small and the numerator is staying the same, or also getting but the numerator is staying the same, then we could say the whole fraction would be blowing up. All right, so this is 0 over 0, which means I either have to do some more algebra or calculate this numerically. So we're just going to do this numerically. We're going to use the table function on the calculator. I'm just going to plug in smaller and smaller values of h. So I'm going to use my y equals and just type in sine of x divided by x and make sure we're in radians. It'll come out differently if we're not in radians. Okay, so sine of x over x, I'm using x's because I don't have h's. Okay. Then I go to my table, and I'm going to type in smaller and smaller values for x. So I might do 0.1, 0.01, 0.001. What does it look like my limit is approaching? Maybe I'll do one more, 0.0001. We'll approach from the other side, -0.1, -0.01. Does it look like my y values, sine x over x, are approaching a specific value? What is that value? 1. Good. So it looks like my limit is 1. So that's an important fact. Now I want to do the cosine of h minus 1 over h. So take a minute and figure that one out using your calculator. All right, what do you get for cosine of h minus 1 over h? It's getting close to 0. Anybody else get 0? Okay. Good. So I have these two limits. These are going to come in very handy when I'm trying to prove that the derivative of sine is cosine. But before I go to the proof, we're going to do a couple of examples where we use these limits, where I make these limits work to my advantage in trying to calculate other difficult limits. So if I want to take the limit as x goes to 0 of the sine of 3x over the sine of 5x, what happens if I just plug 0 in? 0 over 0, right? Sine of 0 is 0, so you get 0 over 0, which means we have more work to do. Okay, so I could do it numerically, which is a perfectly valid approach. Let's do it numerically and see what we can expect. Then we'll do it algebraically and see if we can get what we get numerically. Okay, so we're going to do sine of 3x divided by the sine of 5x. Table, I have x is going to 0, and what does it look like my limit is? 0.6, yeah, 0.6. Okay, so let's see if we can come up with that algebraically. And we're going to use these two limits that we got numerically to help us figure it out. So the sine of 3x, I can take the limit of the sine of 3x over 3x, right? If there was a 3x in the denominator, that limit would be 1, right? Because the sine of something over that same thing is 1. So if I had a 3x in my denominator, then that limit would be 1. But you can't just do that, right? We can only multiply by something that's really 1. Otherwise, I'm changing the expression. So if I multiply this whole thing by 3x over 3x, then I could rewrite it as the limit as x goes to 0 of sine 3x over 3x times 3x times 1 over the sine of 5x. Do you agree that those two things are equal? I just did some algebraic manipulation. Okay. So the reason I did that, it might be unclear, but it will become clear soon. All right, so the limit as x goes to 0 of sine 3x over 3x, what's that? 1. Okay, so that I can just, that's easy. That part's 1. What's the limit as x goes to 0 of 3x? 0. And what's the limit as x goes to 0 of 1 over sine 5x? Or just look at the sine 5x. Limit as x goes to 0 is well, we have 0 over 0, right? I broke these into two separate fractions, but if I multiplied them, it would be 3x over sine 5x, and then I have 0 over 0. 0 over 0, we can't tell what the limit is. Okay, so I helped myself a little bit. What if I had a 5x on top of the sine 5x? What would the limit of that fraction be as x goes to 0? 1, yeah. Right? Flip something that equals 1 over and it still equals 1. So if I had a 5x on top of this, then my limit would be 1. So I now have the limit as x approaches 0 of sine 3x over 3x times 3x times 5x over sine 5x, right? So I moved this 5x into my numerator here, but then I still have a 1 over 5x. So both of these guys are 1. Those are just 1s. The limit as x goes to 0 of them is 1. So I'm left with the limit as x goes to 0 of 3x over 5x. I can cancel the x's. And then what's my limit? 3/5, which is 0.6 that we got numerically. So my trick, the only really tricky thing I did was I multiplied by a fancy form of 1 twice. I multiplied by 3x over 3x and 5x over 5x so that I could take the sine 3x and the sine 5x and write them in the format where I know the limit is 1. All right, here's a tricky one. We want to find a value for the constant k, a non-zero value, that makes this function continuous. So what was the definition of continuous again? You don't have to pick up your pencil. That's a good informal definition. But the sort of calculus-y definition? For every value of x, there's a value of y. That's a good first thought. But you could have a value of x for every value of y and still have to pick up your pencil. Like, right, like, no, tangent of x has asymptotes. So there are places where it has no y value. But yes, the limit has to exist. It has to be the same from both directions and the value of the function. So what you were just saying, though, like this function has a value of y for every value of x, but it's not continuous. So the way we define continuous is that the limit from the left has to equal the limit from the right. So in this case, they're not equal. The limit from the left has to equal the limit from the right, and it has to be the value of the function. So this one fails because the limit from the left doesn't equal the limit from the right. Okay, so for continuity, I want it to be continuous at 0. So the limit from the left, oops, that's not a -1. You just put a little negative. The limit as x approaches 0 from the left of f of x has to equal the limit as x approaches 0 from the right. And when you approach 0 from the right, 3x plus 2k squared, that's a continuous function, right? That is that's a line. If k is just a number, then this is a line. So that means that the limit from the right equals the value of the function. So I just have to worry about this. All right, so if I'm coming at 0 from the left, which function am I following? Tangent of kx over x. So I need the limit as x approaches 0 from the left of tangent kx over x to equal the limit as x approaches 0 from the right. When you approach 0 from the right, which function are you following? Which formula? 3x plus 2k squared. And what is the limit as x approaches 0 of this guy? 2k squared. Because it's continuous, we can just plug the 0 in, and we get 2k. squared. So I need to force the limit as x goes to 0 from the left of tangent kx over x to equal 2k squared. Figure out what value of k will make that true. What value of k will make that true? Think about it for a few minutes. See if you can brainstorm some ideas. We got lots of good ideas. Several people got there. First idea is that take that tangent kx and rewrite it as a sine over a cosine, because we know some limits about sine kx's over kx's, right? Sine h over h we know is 1. So I'm going to take that tangent, rewrite it as a sine over a cosine. Okay, so I'm taking the limit as x goes to 0 from the left of sine kx divided by cosine kx, and that should all be over x, but I could, just a little piece of algebra, I can put that x there. Is that okay? If I do the whole thing, the sine over the cosine is the tangent, whole thing over x, instead of dividing the whole thing by x, I could multiply it by 1 over x, and we would land with this result. So just saving a little bit of time, not writing it all out. Okay. Now, if I had a sine kx over kx, then that limit would be 1, right? So maybe I will multiply this fraction by k over k, because then I'll have a k in the denominator. And I will get the limit as x goes to 0 from the left of sine kx over k times k over x cosine kx. I need that to be a kx, right? Yeah. So I'm going to multiply by kx over kx. There we go. Okay, so this fraction goes to 1. Sine kx over kx goes to 1. And then the fraction on the right, my x's cancel. And I want to take the limit as x goes to 0 from the left of k over cosine kx. So what happens if we just try to plug in the 0? Yeah, then the cosine of kx would be equal to 1. Okay, so the cosine of 0, when I plug in a 0, I'm taking the cosine of 0, and that's a 1. So this becomes a k over 1, or just k, right? And then go back to what I was trying to do. I've been working on this limit the whole time. I've just been simplifying this guy. I simplified it to k, right? It equals k. And I need that to equal 2k squared. I need to find a k that will make that equal to 2k squared. So I need to solve k equals 2k squared. And what do you come up with? K equals 1/2. So k equals 1/2 will make that function continuous. Yeah? What is it? Uh-huh. Putting a k in the denominator? Oh, dividing both sides of this equation by k. Yes. I did see some people doing that, and that's a great idea too. So then you have tangent kx over kx. Right. Kx, and that comes out to 1. Yeah. So that's another way, is instead of just simplifying this limit, you could work this as an equation, right? Divide both sides by k, and now you have tangent kx over kx, and you can simplify that limit from there to 1. So let's take a quick look at this Geometr Sketchpad file to see that 1/2 really does work to make this continuous. I've got my two functions, tangent kx over x. That's the graph that's going to be graphed to the left of 0, so to the left of the y-axis, and then 3x times 2 plus 2k squared, which is what's going to be graphed to the right of the y-axis. So if I graph tangent kx over x, in this case k is 2, right? For right now k is 2. So that's the graph of tangent kx over x, and then I'm going to graph 3x plus 2k squared. That's just a line. I'll just scroll this over. There we go. And I need these two to be continuous at 0. So I need the red to touch the blue at the y-axis at x equals 0. So I'm going to move this slider k equals 2. So you see, as I make k bigger, they get further apart. As I make k smaller, they get closer and closer and closer until k is 1/2. And then they touch. Close enough. Okay, so you can see that it does in fact make the function continuous, where the limit from the left equals the limit from the right, and the two functions touch each other at 0. Yes, that would definitely be a sharp corner. And what does a sharp corner tell you? Not differentiable, right? I can't take a derivative there. It's continuous, but not differentiable. Okay, so we're now in a position where we are comfortable with these new limits, sine h over h and cosine h minus 1 over h. We're going to prove that the derivative of sine is cosine using the limit definition of the derivative. So I'm just going to start on a new page here. Okay, so I want to take d dx of sine x. So the limit definition of the derivative, right? F of x plus h minus f of x all over h. I'm just going to write that out. So I've got sine of x plus h minus sine of x all over h. Okay, so then there is a little formula from pre-calc that you might remember, the identity for the sine of the sum of two angles. Anybody remember what that is? It's written on your paper. So if you wanted to take the sine of a plus b, it's sine a cosine b plus sine b cosine a, right? Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. You guys remember those? Okay. Yeah, it came up. It's okay if you don't remember it, but you just have to remember that there is one, and I'm going to tell you what it is. Okay. So over here, we have a little aside. If you want to take the sine of the sum of two angles, it is sine A cosine B plus sine B cosine A. Okay. So I can't even remember what that is off the top of my head most of the time, right? I just had to read it off the paper. But the important thing is to know that there is one, because when I look at this sine of x plus h, I go, oh, that's the sine of the sum of two things. Isn't there a formula for that? Oh, yeah, I'll look it up, right? So this is going to be, instead of the sine of x plus h, it's going to be the sine of x, cosine of h, plus the sine of h times the cosine of x. And then this is all minus sine x. Right, so that was just simplifying sine of x plus h. Then I have minus sine x all over h. All right, so now I'm just going to do a little bit of algebraic rearranging, and I should have, sorry, I can't believe I forgot to write this. Limit as h goes to 0 of all this. Right, that's an important thing. All right, so I want to simplify this so that I get like a sine h over h or a cosine h minus 1 over h, or maybe both. So ideas. You guys are full of life today. Let's look at this term and this term. They both have a sine x in them, right? Okay. Just write them together. So it's going to be the limit as h goes to 0 of sine x cosine h minus sine x. And then I still have a plus sine h cosine x all over h. All right, so all I did was rearrange the order of the numerator here. So these first two terms both have a sine x. Let's factor it out. Okay. The purpose of factoring it out is that once it's factored out, I'm going to be left with a cosine h minus 1. Right? Hooray, that's what I'm looking for. So this is going to be the limit as h goes to 0 of cosine, oops, I'm factoring out a sine x. Sine x times cosine h minus 1. I'm just factoring out a sine x. And then I still have plus sine h cosine x all over h. All right, so when you have a plus b divided by c, right? When you have a sum in the numerator divided by a single term in the denominator, you can divide it into both pieces. So this is going to be the limit as h goes to 0 of sine x times cosine h minus 1 over h. Is that okay? All right, and then I have plus, put the h into this term, and I have sine h over h times cosine x. And sine h over h, that limit is 1. And cosine h minus 1 over h, what is that? 0. Yep. Looked at that one earlier, and it was 0. So I end up with sine of x times 0, so this whole term just goes away, because x is not the variable that's going to 0 here, right? So h is what goes to 0. So sine of x is doesn't change as h goes to 0. So this ends up just being sine x times 0 plus 1 times cosine x, and I get cosine of x as the derivative of sine x. So it all rests on those two limits. And because when we're in radian mode, these limits are 0 and 1. The derivative comes out all nice and pretty as cosine x. These limits are not 0 and 1 when you're in degree mode, which means that the derivative of sine is not cosine if you're in degree mode. So it actually ends up being cosine times pi over 180. So this is why we always do calculus in radians, because it makes the derivative of sine cosine. Okay, so now in your groups, I want you to take a few minutes and take these two derivatives for practice. All right, let's do these together. So if y is 5x cubed plus 4 sine x, and I want to take y prime, that's a sum of two functions so that I can take their derivatives separately and then add them. What is the derivative of 5x cubed? 15x squared. And 4 sine x? 4 cosine x. Yeah, we just have a constant coefficient. Those just come along for the ride, right? And then you take the derivative of sine, which is cosine. So that one was easy, right? All right, now I have a triple chain rule, right? I have sine of x is my innermost function. Then I've got something to the 7th. And then I've got all of that to the 1/5. Okay, so my outermost function is going to be sine of x to the 7th to the 1/5. So first I'm going to write it like that. Oh yeah, sure. Let's do that. Yeah, why make it harder? That's a good idea. Why apply the chain rule 3 times when we can just simplify the function first? Yeah, I like it. So that is sine of x to the 7/5. So we've got some stuff to the 7/5. Right, so I'm going to apply the power rule to the stuff. So I'm going to have y prime is equal to 7/5 times the sine of x, and then 7/5 minus 1 would be 2/5. So I applied the power rule to my stuff, but then you still have to multiply by the derivative of the stuff, which is cosine x. So that one wasn't too bad either. I was gearing up for a double chain rule. All right, so next we have the graph of y equals cosine x. We're going to start by trying to figure out what its derivative is the same way we started with sine. We're just going to try to sketch a graph of its derivative based on the graph of cosine. All right, so where on the graph of cosine, at what x values do you have derivatives of 0? 0, pi, and 2 pi. Yep. Those are places where you have horizontal tangent lines. That means that the slope of the tangent line is 0, which means that the derivative is 0. So I put zeros at those x values. Okay, take a look at pi over 2. If I were to draw a tangent line at pi over 2, what do you think its slope would be? Looks like it's about -1. And what if I draw a slope at 3 pi over 2? What would that be? Looks like 1. And connect those with a nice smooth curve. And what did I just draw? Yeah, the negative of the sine graph. Sine would start at 1. It would start at 0 and go up, right? This is a reflection of the sine graph over the x-axis, which means that it is the negative sine of x. So we won't go through a formal proof of this one like we did for sine. It's similar, uses those same two limits, and an angle sum formula for cosine. That might be a fun bonus for a test if I asked you to prove that one, because since we didn't do it in class, but it mirrors the one we just did. So these are the derivatives of the 6 trig functions. Derivative of sine is cosine. The derivative of cosine is negative sine. Derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is negative cosecant times cotangent. Memorize these tonight and rememorize them for the next 5 nights. And they should be your best friends for all time, right? You should wake up in the middle of the night and know these trig derivatives. Well, you can bring a note card to class on Monday. Yeah. And I won't put any of the, like, if I put trig derivative, it will be like sine or a cosine or a tangent. If I put one on the quiz. All right, so little trick to help you with derivatives of sine and cosine. Think of this as like a little ladder, right? The derivative of sine is cosine, and the derivative of cosine is negative sine. But then the derivative of negative sine, right, because the derivative of sine is cosine, but then you just carry the negative, right? So the derivative of negative sine is negative cosine. But the derivative of negative cosine would be negative, and then the derivative of cosine x is negative sine x. So that takes us back to the top at positive sine x. Right, so the derivative of cosine x, negative cosine x, is sine x. Okay, so it's kind of like a little ladder. So if I wanted to find the 7th derivative of sine x, I would just follow this. I would go, this is the 1st derivative, 2nd derivative, 3rd derivative, 4th derivative, 5th derivative, 7th derivative, negative sine x. Did I not count to 7? 1, 2, 3, 4, 5, 6, 7. Yeah, negative cosine x. Thank you. All right, and I just told you 6 derivative functions. I only proved one of them for you. So just so you don't think I'm making up the rules, I'm going to prove one more. Let's do tangent. I want to take d dx of tangent x. And I'm going to spare you a limit definition proof. We are going to rewrite tangent as sine over cosine. Then how do you take the derivative of sine over cosine? What would you do? Quotient rule. So how much class do we have left? We've got 15 minutes and a bunch of problems. Okay. I'll just do it then. I won't make you do it at your seats. Okay, so I'm going to apply the quotient rule to sine x over cosine x. The quotient rule says denominator times the derivative of the numerator, which would be what? Cosine x. The derivative of sine x would be cosine x. Okay, so it's denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. What's the derivative of cosine? Negative sine. Right, so denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And what's cosine times cosine? Cosine squared. So this is cosine squared x. And then I have a minus and another minus, right? So that's going to become a plus. Sine squared all over cosine squared x. Can I just cancel the cosine squareds? Easier way, what do you mean? Yes, there's an identity. Cosine squared plus sine squared is 1, yes. But somebody please tell me why I can't cancel the cosine squareds. Why can't I just underneath it also? Yes. Yeah, so you can't cancel when it's just addition, right? If that said cosine squared times sine squared, I could cancel the cosine squareds, but you can't cancel when there's addition. So use the Pythagorean identity, right? Cosine squared plus sine squared is 1. Talked about that yesterday or Wednesday. So I have 1 over cosine squared, and 1 over cosine, reciprocal of cosine was which trig function? Secant. So I have secant squared x is my derivative of tangent. So proving any of the other 4 that remain, or 3 that remain, using a quotient rule or a power rule and a chain rule would also make a good bonus test question, or just a test question. Okay, so now I would like you to spend the last 10 minutes working through these last few problems.